Hey, P Statistics. So today we're going to get into the second part of section 5.2 on probability rules. So this just a real quick, let's take a review through the rules we've got so far from the first section. So first of all, the probability of any event, an event is maybe a set of outcomes that meet some certain condition. We use this notation P of A, P parentheses A. So probability of the event A is always going to be a number between 0 and 1. 0 is impossible, 1's guaranteed. If S is the sample space of all the possible outcomes, the probability of the sample space is 1. That covers all possible outcomes. If you're dealing with equally likely outcomes, which is when we're in kind of simple probability mode, equally likely outcomes, then it's just the number of outcomes in the event, so the number of favorable outcomes out of the number of possible outcomes, the total number in the sample space. If you want to know the complement, the probability that something doesn't happen, you can do 1 minus that probability. So if something has a 40% chance of happening, it has a 60% chance of not happening. And that's that little C, that complement. And then if we're dealing with mutually exclusive events, two events that can't occur simultaneously, there is no overlap between their outcomes, then we can just add their two probabilities. And so this is if it's an or statement, sorry. If the addition rule is when you're dealing with or. If it's probably A or B, you can just add those two together. But we'll see here shortly that that's only in that situation if that's our case. All right, so what if that's not the case, and what can we do? So we're going to use two-way tables and so on, and the Venn diagrams and things like this, like that, to model this stuff. So first of all, or, I want to make sure we're clear. When we say or, sometimes in everyday life, there's two different meanings. There's two different types of ors. There's the or, where if you're at a restaurant, the waiter asks you if you want soup or salad. You have to pick one or the other. That's an exclusive or. It's either or, but not both. There's also this or of, do you want cream or sugar with your coffee or whatever. And in that case, it's okay to say both. So if the waiter asks you for soup or salad, you can't say, sure, that sounds good, both of those. You have to pick one or the other. So when we're talking about or, our or is going to be the inclusive or, where you can also have both. And so that's the one that's meant in statistics. A or B means one or the other or both, right? So keep that in mind. When you're trying to find probabilities involving two events, like probability of A or B, a two-way table can display the sample space in a way that makes the probability calculations easier. So kind of getting back to two-way tables from all the way back in chapter 1. So let's look at an example problem here. Students in a college statistics class wanted to find out how common it is for young adults to have their ears pierced. They recorded data on two variables, gender and whether or not the student had a pierced ear. For all 178 people in the class, the two-way table summarizes the data. Suppose we choose a student from the class at random, define event A as getting a male student, and event B as getting a student with a pierced ear. All right, so here's our two-way table of all of our students. So we're going to pick one student out of these 178. So that's our sample space, is actually 178, and each individual has some information about them. And so we have kind of all those possible outcomes, but we've organized it. We have all of our males organized into this column, all of our females organized into this column, and then whether or not they have a pierced ear for these rows. So they want to know, find the probability of B. B was the event that the student has a pierced ear. So we're just focused on one of these things. We're just focused on whether or not they have a pierced ear. So this is kind of like we had like marginal relative frequencies. That's really what we're dealing with here. We had conditional and and so on and so forth. So this is a marginal relative frequency, actually. So to find the probability of B, pierced ear. So there are 103 pierced ears out of 178 possible in our sample space. And again, we're choosing at random, so all the students are equally likely to be chosen. So there's our probability, 0.579 or 57.9% chance. So then we want to know what's the probability of A and B, and then also interpret that value. So I want that the student is male and has a pierced ear. So our males, and so this is a joint frequency, if we want to get back to those terms from that. I want male and pierced ear. That's these 19, but that's out of everybody 178. And so that is the probability of getting a male with a pierced ear. That 19 out of 178 gives us about a 10% chance, or 11%. All right, and then, so yeah, if we're interpreting that, about 11% chance of randomly selecting a student that from this class that is male and has a pierced ear. And then they're going to change this up on us and throw that into an OR. And so I'm going to find that probability and maybe also be able to interpret that as well. So in this case, we have that either they are male, which would include these 19 and those 71. So we see those numbers down here. And then also includes the females with a pierced ear. So I want male or pierced ear. So we could do it that way. We could add those three numbers up, put them over 178, and that gives us our probability, a 97.8% chance, almost 98% chance. Basically, any but these four girls that don't have pierced ears. Basically, that's what this or means. They're all of our males or people with pierced ears. So that's one way we could approach it. Another way is like this. We could also think about the total number of males, right? So we have the total number of males here is 90. And so like the probability of A was 90 out of 178, and then the probability of pierced ear was 103 out of 78. Well, we can't just add them here. We can't just add them like we did before. We had that addition rule that worked when they were mutually exclusive. Well, these aren't mutually exclusive anymore because there are males with pierced ears. These 19 would get double counted if we added these two probabilities together. If I added this 90 plus 103, in fact, you'll realize very quickly it doesn't make any sense because that number ends up being bigger than 1. So that's where we end up, yeah, if we did that, we end up double counting this group if I include them in those 103 and include them in this 90. So we need to make sure that we don't do that. So we can fix double counting problem by subtracting that group that was double counted. And so this is kind of developing our other formula. What we can do is the probability of getting a male or a pierced ear is we're going to add up the probability of a male, which is this 90 out of 178, plus the probability of female, 103 out of 78, but subtract the 19. That's another way of doing it and getting to that 174 out of 78. We could have also just added the 71, the 19, and 84, but this rule ends up being really nice because it's, we don't have to figure out all those specifics. We can just work with the probabilities we got. So ultimately, we can get to a general addition rule. If A and B are two events resulting from some chance process, the general addition rule says the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Let's see, there it is, minus the probability of A and B. All right, and this is a general addition rule. Our other addition rule was for mutually exclusive events. This one actually works no matter what, which is why this is the one that actually shows up on your formula sheet. The probability of A or B is always going to be the probability of A plus the probability of B minus the overlap. It just so happens that when there is no overlap, there's nothing to subtract, and you can just add the two. So if I wanted to know the probability of like getting a 5 or a 6 on a die, I could add the probability of 5 plus the probability of 6, but there's nothing to subtract because there's no way to get a 5 and 6. In this case, male and pierced ear is possible. So that's what we're dealing with there. All right, so an example of this, a survey of all residents in a large apartment complex reveals that 68% use Facebook, 28% use Instagram, and 25% do both. Suppose we select a resident at random. What is the probability that the person uses Facebook or uses Instagram? So we could create a two-way table of all this and so on, but we don't have to. We can just use our new general probability rule where we can add the two and subtract the overlap. So if event F, if we let that be that they use Facebook, and so the probability of F is 68% use Facebook, and then I is Instagram, so probability of I is 28%, and then 25% do both. Basically end up with 71% once we add those up and subtract that. You could also think of it as like, oh, well, there's, an additional like 3% here in Instagram that don't use Facebook that we end up adding on there. It's, a couple of other logical ways we could look at it. But that would ultimately be that probability.